Thanks for attending my virtual presentation. And hi to everyone. What I will be going through today in this session sponsored by Sapidine is going through the strategies what we use to screen for selecting high affinity antibodies in our antibody therapeutic programs. The main agenda would be how the antibodies are, why as a human therapeutics, and what is our screening workflow, then how we use affinity screening, and before that, the basics and methodologies we use, and what could be the right affinity method to choose for screening the leads. And then I will end up with recently we developed a high throughput KinExA for screening molecules with very high affinity, and end up with some summary. Why antibodies are good therapeutics? We know the antibodies through the antigen binding region binds specifically to the target and neutralize it or enhance activity or whatever it is. And then they have a large half-life because of the Fc molecule present in the antibody. So they are all good therapeutics because of low off-target toxicity and high specificity and long half-life. When we generate antibody, there is a big screening process. First, we use genomes to immunize the genomes to generate antibodies, look for titers from the genome's blood, and then select purify the B cells and make hybridoma. We get from the hybridoma thousands of binders to the target, and from there we do some primary screening and secondary screening, and then sequencing of the leads. During that process, from thousands of binders, we use different activities, epitope bindings, sequence diversity, screen for, and we get hundreds of antibodies with the required specificity and multiple epitopes and diverse antibodies. At this stage, we use the affinity screening for the design goal. Often our design goals are less than 100 picomolar affinity range. So we use different affinity screening platforms to select the top 10 leads which will go for early optimization. So what is the relevance of the affinity screening in the lead panel selection? Earlier, we use the affinity measurements for the assay development. For example, what platform, I will go through the different platforms in a later slide, but what platform we should use for the affinity screen, and also using a benchmark antibody, we determine CET affinity. So when we are screening, we know our molecules are in relation to that benchmark affinity, where it stands. And also it will help us to set us the sensitivity of the bioassay and other binding assays. During screening, what we use this affinity screening is to call out the very bad affinity molecules at the outsteps, and also we could screen for either on-rate related or off-rate ranking, or choose the relatively high ranked antibodies within related bins, which has good potency and binding. At a later stage, affinities are used for lead characterization. In the lead characterization, it would be to determine the affinity number, what they are, and that would help us to select the antibody which is better than the design goal, let's say, and also we will do affinity characterization on the Tascalisi species. In general, most of the time we determine affinity for both human and cyno to determine the gap, and so that we could use as the preclinical model. Just to give some basics so that why we need to choose different affinity technologies or instruments. So we know that if an antigen binds to an antibody, it forms antigen-antibody complex, and in the beginning, the antigen and antibody would be in high concentration, and the product would be formed based on the on rate. And once the product is formed, then it also can dissociate to make antigen antibody, which is determined by the K-off or dissociation rate. So one can measure the on rate or the association rate and the dissociation rate kinetically as soon as you mix the antigen and antibody. And from there, we can calculate the KD or the affinity, or one can leave the reaction go to equilibrium, and at equilibrium, we can measure the concentrations of the reactants or the product, and from there, we can calculate the KD too. So basically, the affinity can be determined by measuring the kinetics or the equilibrium concentration of the biotic partners. So these are two different technologies we could use to have an information on affinity. The kinetic measurements are done by technologies like SPR or BLI, where one of the reacting molecules is adsorbed or bound to a surface in SPR and BLI, and the other molecule is passed through the column where it can bind, and while it is binding to the attached molecule, we can measure the on rate, and after that, if it is just leave it in buffer, then it will dissociate from the product form, and we can measure the off rate. From there, we can calculate the KD. The advantages of this SPR and BLI are, say, kinetic information can be gathered quickly within a few minutes, and most of the instruments are high throughput enabled, so we can screen hundreds of molecules at a time. But there are some issues on this technology, on the kinetic measurement technologies. Generally, we need purified materials, and we need to know the concentration. If the molecule is partially denatured, especially the molecule which we are passing through, if it is partially denatured, then we cannot calculate the exact KD. And in many instruments, the off rate determination would be limited if it is having a slow off rate than let's say 10 power minus 5 or so. The other important thing is for membrane targets or on-cell targets, it's hard to flow the cells in the instrument, and people try to purify the membrane targets. For not all, it's good because it's hard to purify membrane targets often, and also it's hard to have the active concentration of the purified molecule. The other technology we use for measuring the affinity is solution-based affinity measurements, where you could measure the concentration of the reactants or the products, and from there you can calculate KD. We use KinExA for that, in which both antigen and antibody are taken in solution, and when the complex is formed and equilibrium is reached, so the concentration of the free concentration of antigen or antibody or the product is in equilibrium, so that concentration will not change. So what we do is we titrate a constant amount of antibody with antigen and leave it to equilibrium. The equilibrium solution is passed through a column where we take beads coated with the antigen. So when this mixture goes through this column, only the free antibody would be captured by the antigen coated on the bead, and that capture concentration depends on the amount of free antibody present here. Then with the secondary antibody labeled, we can generate a binding curve based on the antigen concentration we have and the free amount of antibody present. And this binding curve will give the KD of the reaction. So this way we could use KinExA and measure the affinity. The advantages are the purified protein is not absolutely needed. We can just pause or titrate from solution which is not purified. So not the concentration of both the binding partner is not absolutely necessary. If you know one of the binding partners concentration, that should be enough. And this is ideal for the membrane proteins from on-cell targets, if it is purified and partially purified or so, or even directly on-cell we could use. And this is an alternative method, definitely, if coupling or capturing of a binding partner in solid phase impacts their kinetics. And also, if the dissociation constant measurement or dissociation rate measurement is limited by the other instruments, this is the best one. The disadvantage is it is not at high throughput enabled, and even though we could measure the affinity of the reaction for on-cell, it could be an avidity interaction, so it cannot differentiate the avidity versus affinity. To summarize, so SPR or BLI instruments like Biocore, Kaptera, or Octet, they could be used by measuring kinetic measurements, in which one of the material is attached to a solid surface, and hence influence of substratum is possible for that. Basically, in these kinetic measurements, we measure the on rate and off rate, or K on and K off, and the KD is calculated. Whereas in solution equilibrium measurements like KinExA, it is equilibrium measurement, both are in solution, no influence of the substratum, and we measure the KD and on rate. Off rate can be calculated from the measured KD and on rate. So the other important thing to remember before screening and the instruments used, as I said, soluble or on-cell targets could influence our selection. And again, the soluble targets, if it is monomer, dimer, or trimer, then if it is monomer, it's fine, but if it's a dimer, then if you capture the antibody on the surface and flow the dimer, then it could be avidity information for both dimer and trimer. For membrane cell targets also, it could be a monomer or a heterodimer or a homodimer or trimeric molecules present, and depending upon the nature of the target, it could be affinity or the ability measurements we will be doing, which is important to know. Now, I will just give some examples in which we use different technologies for our advantage and for the purpose. For example, if the antigen is a soluble target and it is secreted and it is purified and we know the concentration for sure, and if we need to screen hundreds of molecules, say up to 1,000, let's say, and our goal is to cull out the bad ones. Say, for example, just if you want to know how many from that panel is having better than 1 nanomolar affinity, then we could use either one of these Bayeko, Octet, or Katara and generate binding curves, and to know the less than 1 nanomolar affinity, these two antibodies are having 1 nanomolar affinity, and this one is not. With this information can be obtained easily from the kinetic measurement instruments. Also, if you want to know quickly the affinity difference between the orthologs, for example, human and cyno, whether they are similar or not similar, then also this kinetic measurement technology and instruments would help quickly to understand that. If we are screening for off-rate one, say just screen off the bad off-rates or the fast dissociation molecules, then we could quickly screen for that, because generally this screening we do at 10 minutes dissociation. To have 10% dissociation, anything better than 5 to the e to the power minus 4 would be screened easily by kinetic measurement instruments. For all these, we will not use KinExA because that is low throughput and it will take time to measure or screen. If the material is soluble but only partially active, and if the size is, when panel size is not hundreds, and also if molecules having a very slow off rate, say even after 30 minutes, if you are not getting a good off rate, then for those kind of molecules, we use KinExA to generate binding curves, one at antibody taken at KD concentration and another one at higher than KD concentration, and with titrating antigen, binding curves can be generated, and from these we can have the KD information, that is 36 picomolar, and also from this curve the KinExA software will generate the percentage activity of the antigen. So in this example, our KD is 36 picomolar and the antigen activity is 71%, and we didn't get appreciable dissociation. That's why we could not measure the exact KD in kinetic instruments. For on-cell targets, it is the KinExA method we use for very high affinity measurements. Here we need not purify the target. We equilibrate cells, titrating cells with a constant amount of antibody, and at equilibrium, we separate the free form and the bound form by centrifugation, and then use KinExA to measure the free antibody concentration. And on the right, an example for human ORA1, we measured the affinity in a low picomolar range, and also we could measure the expression level of the target on these cells as 2 power E6%. So both KD information and the expression level can be calculated without purifying just by using on-cell in the KinExA platform. When the antigen is secreted and if it is not purified and if it is having very low concentration, then still we could use KinExA to measure high affinity interactions. In this case, reverse format KinExA is being used. For example, generally we titrate the antigen and use a constant amount of antibody. For the reverse format, it is reversed. The antibody is titrated and equilibrated with a fixed concentration of antigen, and at equilibrium, this remaining free antigen need to be measured. For that, what we do is we coat the beads with the antibody which we are using in the equilibrium and capture the free antigen, and using an antibody which is not competitive to the antibody of our interest, we can label that, and using that we can measure the free form of the antigen and measure the KD. Here is an example where we just having a cultured media which has IL-13, and we just diluted the IL-13 cultured media from neat or 11-time dilution to 550 times dilution. And then when we dilute, the antigen concentration, the fixed antigen concentration is keep decreasing whatever fold, and we could generate binding curves, and using KinExA software, we could calculate the KD and as well as the concentration of the antigen. When we did that, the KD is really very high, 9.4 picomolar, and we also checked with recombinant IL-13. Its affinity is similar to that, and also the concentration of IL-13 present in our cell culture media is about 31 nanogram per ml. So to summarize, we could use kinetic measurements, instruments like Biocor, Cotera, Octet. That's what at our site we use for all soluble targets. When we want to screen hundreds, and if we have purified soluble targets available and concentration known, and generally screen for anywhere from 100 picomolar to micromolar, and screen out the bad ones from there. The same soluble targets, but if the concentration is not known or only partially native, and or if they have very slow dissociation kinetics, and if the number is low, then we use KinExA to measure the affinity in the sub-picomolar to nanomolar range. But most of the time we use this first to nail down the molecules to tens from thousands, and then use KinExA to measure the very high affinity or rank the very high affinity ones. So if these are all 5 for soluble targets and non-soluble targets, whatever I said, to screen for molecules having 100 picomolar range by using the Cartera octet or Biocor. And then if it is very high affinity, we could use KinExA to measure the affinity to select the EO leads. But many times we may have many molecules coming at range of hundreds or better than 100 picomolar. Then we cannot use the screening platform of the kinetic instruments. So for that, what we did recently was to develop a method for a little bit high throughput KinExA for measuring very high affinities. It's called a single concentration inhibition method. I will just go through briefly how it works. So if you understand the kinetic equilibrium, KD is antigen concentration multiplied by antibody over the product, or the antibody concentration at equilibrium would be equal to KD multiplied by antigen, antibody, or the product over antigen. By rearranging the equation, for a given KD, the initial concentration of total antigen required to give 50% free antibody at an initial concentration of total antibody can be calculated by antigen total equal to KD plus half antibody total in the initial time. So for example, if we need to have a KD cutoff of 100 picomolar, if we equilibrate the antibody with a KD concentration, let's say 100 picomolar, then we need 150 picomolar of initial antigen concentration, so that at equilibrium 50 picomolar of antibody can be present free. And to have the best sensitivity to KD, the total antibody taken at the equilibrium should be either equal to or less than KD concentration. So what we did was, we took a panel of membrane target which was purified. So it's a soluble target, but it was a membrane target which we purified. We choose an KD cutoff of 100 picomolar. We equilibrate the antigen at 100 picomolar, antibody at the desired KD cutoff of less than the KD cutoff, that is at 20 picomolar, with and without antigen, and then for having non-specific binding calculation without antigen and without antibody buffer load. So after equilibrium, the free antibody was measured in KinExA. Then we calculated the free fraction or inhibited free fraction by determining the signal in KinExA we obtained for antigen inhibited sample of antibody divided by the signal obtained by the 100% antibody, and rank the maps based on the inhibitory free fraction we obtain. Generally, lower the IFF, it is higher the affinity. So we also did full KD curve experiments with low throughput way, and then see if our ranking by this one concentration or single concentration inhibition rank as if we measure the full KD. So from the panel, we calculated the inhibitory free fraction for a number of antibodies and ranked the lower the free fraction, the higher the affinity, and so on. And we ranked about 21 antibodies. And when we measured the real KD, the high affinity ones are really ranked high, and the lower affinity ones are really ranked low. So this free inhibitory single concentration inhibition method do work for ranking a panel of antibodies in a little bit high throughput way in KinExA. So in summary, it is important that we have selecting the right antibody with right specificity and affinity, and depending upon the molecule's nature and affinity range, we have to choose the right technologies, or we can use wisely that the high throughput ones to get range of high affinity ones, and then use the KinExA method to further rank them. That I would like to acknowledge our colleagues at Amgen British Columbia Antibody Discovery, especially Lydia, Vadim, and Christy, who are all doing affinity work at our site. Ian Force and Chadwick, my reporting managers. And I would like to thank Steve Lucky and Tom Glass from Sapidine, who helped me to put together the high throughput or single concentration inhibition method into work, and helped a lot. With that, thank you a lot. And if I have any questions, I would like to take that.